Okay, so section 6.3 I have split into three different parts. Section 6.3 is titled The Fundamental Theorem of Calculus and the Definite Integral. And up until now, we have studied indefinite integrals and kind of filled our toolbox with different methods for evaluating indefinite integrals and coming up with the general antiderivative of a function. And we're going to still continue using those rules. In part 1 of section 6.3, we're going to look at estimating the area between a curve and the x-axis on a closed interval, and also defining what a Riemann sum is. Now, the area problem is to definite integrals what tangent and rate of change problems are to derivatives. So remember, when we were studying derivatives, we first figured out how to find a derivative and what a derivative is, and then we studied some applications. So like the applied optimization problems where we are trying to maximize or minimize a quantity, we fell back on our knowledge of derivatives and using calculus to identify characteristics about functions. Like we determined where the function was increasing or decreasing, which then helped us identify extrema, so maximums or minimums, and then that ended up translating over to our application. So the same thing is going to happen here in our study of definite integrals, but the area problem is to definite integrals what those tangent and rate of change problems were to derivatives. So let's say that we have a function f of x, and it's just to make this simple for starting, let's say that function f of x is a non-negative continuous function on the interval from a to b. And I have a picture here drawn. And let's say that we want to determine the area of the region that's bounded between the function and the x-axis. So that would be from a to b, everything in here, okay? Before we actually calculate the exact area, we're going to start by estimating the area under the curve by calculating the sum of the areas of adjacent rectangles, so rectangles that are next to each other. We're going to start by partitioning the interval from a to b into n subintervals, and then each subinterval will have a length of delta x. And we can find the width of each subinterval by taking b minus a and dividing it by n. Now you can have 2 subintervals, 3 subintervals, 4 subintervals, however many subintervals you want to use will determine the number of rectangles that then you calculate the area of. So for the picture that I have drawn here, I have divided the interval from a to b into 4 subintervals, meaning for n equal to 4. So if I wanted to find the width of each subinterval, I would take b minus a and divide it by 4. So this width here would be a length of delta x. This width would be a delta x, a width of delta x. So with that one, and so with that one. So the width of each subinterval is delta x. So I have that same picture drawn multiple times, and delta x ends up corresponding to the width of the rectangles, of each rectangle that we're trying to find the area of. So in this case, again, we're using n equals to 4, so we're constructing 4 rectangles. So b minus a divided by 4 is actually the width of each rectangle. And there are 3 different common ways of calculating the heights of the rectangles, right? Because to find the area of each rectangle, we need the width and we need the height of the rectangle. There's the midpoint, using the midpoint of the subinterval, of each subinterval, the left endpoint of each subinterval, or each right endpoint of each subinterval. And I'm going to show you how you could do that. So finding the height of each rectangle using each of those different methods. So first, let's start by using the midpoint to find the height of each rectangle. So I'm going to use orange. So this is going to be an approximation of the area bounded between the curve and the positive x-axis, because we're calculating the sum of the areas of the rectangles that we're constructing, and you'll see from the picture that why it's going to be an estimate. Okay, so let's look at the first subinterval. So from A to x sub 1, the width of the rectangle would be delta x. If I'm using the midpoint of the subinterval, I'm going to call the midpoint, which would be halfway between A and x sub 1, I'm going to call that m sub 1 for midpoint. So the height of the rectangle is going to come from evaluating the function f of x at that midpoint, m sub 1. So that point on the curve would be m sub 1 comma f of m sub 1. And then I could draw my rectangle, so the height corresponds to that point on the curve. So that rectangle has a width of delta x and has a height of f of m sub 1. So I'm going to write that over here. So delta x times f of m sub 1 would give me the area of the first rectangle. Then we move to the second rectangle. The second rectangle will again have a width of delta x. I'm going to use the midpoint of that subinterval, which I'll call m sub 2, which would be halfway between x sub 1 and x sub 2. The point on the curve would be m sub 2 comma f of m sub 2. So f of m sub 2 would correspond to the height of the rectangle. And you can already see how, like, this corner over here is going over the curve, and then we're missing kind of this corner right here. So you can start to see why this is going to be an estimate of the area. So going back over to my equation here, I would have delta x times f of m sub 2. That would be the area of the second rectangle. And then I go to the third subinterval. The midpoint I'm going to call m sub 3. The point on the curve would be m sub 3 comma f of m sub 3. Okay, so the area of that third rectangle would be delta x times f of m sub 3. And the last rectangle, m sub 4 would be the midpoint. The point on the curve would be m sub 4 comma f of m sub 4, not 2, 4. And the area of that last rectangle would be delta x times f of m sub 4. Now notice that you could also factor delta x out. So then the area, the approximation of the area would be delta x times the sum of all the heights of the rectangles. Okay, whenever we use the left endpoint, of the subintervals to find the heights of the rectangles, use purple this time, so it's still an approximation. So looking at the first subinterval, so a to x sub 1, the left endpoint of the subinterval would be a. So I'm going to use f of a as the height of the first rectangle, and the width will still be delta x. So delta x times f of a. And then the next rectangle would have a height of f of x sub 1. I'm using the left endpoint of that next subinterval. So that point is x sub 1, comma, f of x sub 1. So the area of the second rectangle is delta x times f of x sub 1. And then x sub 2 would be the endpoint of the third subinterval. So f of x sub 2 would be the height of the third rectangle. And f of x sub 3 would be the height of the fourth rectangle. And then you could probably figure out for right endpoints, we're just using the right endpoints of each subinterval for the height of the rectangles to find the height of the rectangles. Here I'll use blue. Okay, so looking at that first subinterval, the right endpoint would be x sub 1. So that point on the curve would be x sub 1, comma, f of x sub 1. So f of x sub 1 is going to correspond to the height of the first rectangle. So the area of that first rectangle would be delta x times f of x sub 1. The second rectangle would have a height that would correspond to f of x sub 2. And the third rectangle would have a height that would correspond to f of x sub 3. And the fourth rectangle would have a height that would correspond to f of b. Okay, and you could see that none of the endpoints give us an exact area, right? It's an estimate because we're just adding up the areas of rectangles, and those rectangles don't fit perfectly underneath the curve. It does look like, however, that in this case at least, that the midpoint is probably the closest to the actual area under the curve. So let's look at an actual example with a function and use each of those different, so midpoint, left endpoint, right endpoint, for finding the heights of the rectangles and see what gives us like the closest estimate of the area under the curve, okay? So for the function f, we want to find the area between the function f of x equals to x squared plus 1 and the x-axis on the interval from 0 to 2. So let's go ahead and draw that curve. So I'm going to do 1, 2, actually 1, 2, 3, 4, 5, and then about 1, 2. So from 0 to 2, this is x squared, so the parabola shifted up 1 unit when x is 0, y is 1, when x is 1, y is 2, and when x is 2, y would be 5. Okay, and I'm going to actually copy, oh no, I'm going to copy and paste because we're going to be using the same graph multiple times. Okay, paste, there we go. Okay, so we're again going to use n equals to 4, meaning we're going to create 4 rectangles. And let's figure out what the width of each subinterval would be on the interval from 0 to 2, which would also correspond to the width of each rectangle. So delta x in this case is going to be 2 minus 0, that's b minus a, divided by 4. So each rectangle and each subinterval will have a width of 1/2. Okay, so I'm going to add 1/2, 3/2 on here. Okay, so let's first use the midpoints of each subinterval to find the heights of the rectangles. So let's look at the first. Okay, so the midpoint, halfway between 0 and 1/2 would be 1/4. Oops. So we would want to use f of 1/4 as the height of our rectangle. So delta x is 1/2 and then times f of 1/4. So we plug 1/4 into our function to find out what the height of that rectangle would be. And putting that into my calculator, it looks like I get 1/4 comma 1.0625. Okay, and then I move on to the next subinterval. So from 1/2 to 1, the midpoint there would be 3/4. So f of 3/4 is going to be the height of that rectangle, the second rectangle, which if I put 3/4 into the function, it looks like I end up with 3/4 comma 1.5625. And then I move on to the third subinterval. Halfway between 1 and 3/2 would be 5/4. And to find the midpoint, you can just take the average of the endpoints of the subinterval. So the average of 1 and 3/2. So 1 plus 3/2 divided by 2 would give us 5/4. So f of 5/4 will be the height of our third rectangle. And when I plug 5/4 into my function, I get 2.5625. And our last subinterval, so 3/2 to 2 7/4 is going to be the midpoint on that subinterval. Give myself a little extra room here. So 1/2 times f of 7/4 would give us the area of that last rectangle, and that point on the curve would be 7/4 comma 4.0625. Okay, so I can factor the 1/2 out here. F of 1/4 I said was 1.0625. F of 3/4 was 1.5625. F of 5/4 was 2.5625. And then F of 7/4 was 4.0625. And when I put that all into my calculator, I get approximately 4.625 as the approximate area under the curve. So using the midpoints of each subinterval to help me find the heights of the rectangles. So let's look at estimating the area using the left endpoints of the subintervals to find the heights of the rectangles. Okay, so delta x, the width of the rectangles, will still be 1/2. And 1/2, 3/2. Oops. Okay, so using left endpoints, that means I would use 1/2 to find the height of the first rectangle. So it'd be 1/2 times f of 1/2. And then I would use 1 to help me find the height of the second rectangle. So 1/2 times f of 1. Three halves to find the height of the third rectangle. So 1/2 times f of 3/2. And 2 to find the height of the fourth rectangle. Okay, so that would be 1/2. I'm going to factor the 1/2 out. f of, oh, I just used the right endpoints, didn't I? Okay, so I'm going to change this. This will be using the right endpoints. Brain fart. Okay, so using the right endpoints, f of 1/2 is actually 1.25. F of 1 would be 2. F of 3/2 would be 3.25. And f of 2 is 5. So the area ends up being approximately 5.75 when we use the right endpoints of the subintervals. Okay, now let's actually try the left endpoints of the subintervals. I apologize, you guys. Okay, so to find the first rectangle, the height of the first rectangle, I'm going to use 0. Okay, the width of the rectangle is still 1/2. So our area will be approximately 1/2 times f of 0. And then the next subinterval has a left endpoint of 1/2. So f of 1/2 will be the height of the second rectangle, and f of 1 will be the height of the third rectangle. And f of 3/2 will be the height of the fourth rectangle. So factoring the 1/2 out, f of 0 is 1, f of 1/2 is 1.25, f of 1 is 2, f of 3/2 is 3.25. So we get that area, when we're using the left endpoints of the subinterval, is approximately 3.75. So these numbers are pretty different. So midpoint, so just looking at the rectangles that we drew, again, it looks like the midpoint is probably going to be the most accurate for the actual area bounded between the curve and the x-axis. It looks like using the right endpoints is probably going to be an overestimate of the area, and that using the left endpoints is probably going to be an underestimate of the actual area. So the exact area is actually 4.66666, repeating. So using the midpoint, if we look at those 3 different areas, right, using the midpoint was actually pretty close, the midpoints, to find the area. So remember, the midpoints of each subinterval helped us to find the heights of the rectangles. So how can we get a better approximation of the area? Well, let's look at just the midpoints. 4.625, we're pretty close to the actual area of 4.6 repeating. But to get an even more accurate estimate of the area, we could think about making more rectangles. I know you guys have probably all been thinking this in your head, but we can make more rectangles. So increase the value of n, increase the number of subintervals. So if we increase n, that will lead to making more rectangles. Which would end up giving us a better approximation of the area. So like if we had used n equal to 5 and made 5 rectangles, or calculate the area of 5 rectangles, or 6 rectangles, 7 rectangles, 8 rectangles, we would end up getting values, estimates for the area that are closer and closer to the actual area that's underneath the curve. This leads us to the general form of a Riemann sum. So the general form of a Riemann sum for a function f of x, which is continuous on the interval from a to b, is this. So this should look very familiar. Delta x, which is the width of the rectangle, of each rectangle, okay, and then f of c sub 1 plus f of c sub 2 plus f of c sub 3. These are each the heights of the rectangles. So we have been using Riemann sums in order to estimate the area under the curve, or bounded between the curve and the x-axis. Okay, and if we want to use a Riemann sum to estimate the area between 4 minus x squared in the x-axis on the interval from -2 to 2 with n equals to 8. We're going to use the height of the we're going to let the height of the rectangles be f of x evaluated at the midpoints of the subintervals. Remember, when we use the midpoints in our other examples, that gave us a pretty close approximation. So I'm going to draw 4 minus x squared on the interval from -2 to 2. So it's a parabola that's opening downward and has been shifted up 4 units. Okay, so if we plug -2 and we get 0, if we plug -1 in, we would get 3. 0, we get 4. If we plug +1 in, we get 3. And we plug 2 and we get 0. Okay, so we want to let n equal to 8. Okay, meaning we're going to create 8 rectangles. So delta x would be 2 minus -2, that's a minus b, divided by 8, which ends up again being 1/2. So the width of each rectangle is going to be 1/2. Okay, so that means that we want to use -3/2, -1/2 on here, +1/2, +3/2. Let's go rectangle by rectangle for determining the area. So if we're using the midpoint, halfway between -2 and -3/2 is, which -3/2, remember, can be written as -1.5, is going to be -1.75. Okay, so we want to use -1.75, or f of -1.75, to find the height. So our approximation for the area will be -1/2 times, not -1/2, sorry, +1/2 times f of -1.75. Halfway between -3/2 and -1 is -1.25. So the height of our second rectangle is going to be f of -1.25. So 1/2 times f of -1.25 will give us the area of our second rectangle. Halfway between -1 and -1/2 is going to be -0.75. Oops. So the area of our third rectangle is going to be 1/2 times f of -0.75. And halfway between -1/2 and 0 is -0.25. So the area of our third rectangle would be 1/2 times f of -0.25. Halfway between 0 and 1/2 would be 0.25. You can see it looks like we're making a little pyramid. So the area of that fifth rectangle would be 1/2 times f of 0.25, or f of 1/4. And then halfway between 1/2 and 1 would be 3/4, or 0.75. So the area of the sixth rectangle is 1/2 times f of 0.75. Halfway between 1 and 3/2 would be 1.25. So 1/2 times 1.25, sorry, 1/2 times f of 1.25. And then that last rectangle, the midpoint between 3/2 and 2 is 1.75. So 1/2 times f of 1.75. And we can think about factoring 1/2 out. And I already calculated these values, so I have 0.9375 plus 2.4375 plus 3.4375 plus 3.9375 plus 3.9375. So now we're going into quadrant 1, those rectangles in quadrant 1, plus 2.4375 plus 0.9375. Those are all the heights. And we get approximately 10.75 as the area. So it's an approximation of the area between 4 minus x squared and the x-axis. So note, the easiest way to get a better approximation of the area is to make more rectangles or increase the number of subintervals. And we discussed that already. So the actual area under the curve, and whenever we say increase n, right, this should sound kind of like a limit. So if a function y equals to f of x is non-negative and continuous on the interval between a and b, then the area under the curve is defined to be the limit as n approaches infinity of s sub n. S sub n, remember, is the Riemann sum. It's the area of the rectangles. So if we were to think about creating more and more rectangles, so infinitely many rectangles, that would end up giving us the area, the exact area under the curve. So an extra note, in general, Riemann sums can be defined for any continuous function, not just positive functions. So you can also have functions that dip below the x-axis. For those functions that are negative on some intervals, some of the rectangles may be below the x-axis, and you can always think of that as like negative area. Riemann sums may be defined when the subintervals are varying widths, where delta x does not have to be equal for each subinterval. So basically you could vary the width of each rectangle to make the rectangles like fit better underneath the curve. However, we're not going to actually do that in this class. Okay, so